Hello, fans of GeoGebra. I will walk you through a tutorial on the algebraic part only. I don't think we'll have any graphics at all except for inserting some pictures. And I think what you will find is that the power of this children's program is astonishing. I'm using it for everything that I do now, and I want you to use it also. I use Classic 5, which I highly recommend. I'm not an expert at all on the other versions. This one does get updated, and this one is perfect as far as I'm concerned, except for one or two little things that drive me bananas. When you open it up, you get an algebra window and a graphics window, or a geometry window and an algebra window, and that is the name, geometry and algebra. I will do a few things right now which you should do also. You don't have to change the font size, but I will because this is a video. So I'm going to increase the font size so you see it a little better. And then I do think you should do this. Turn off the labeling because everything gets labeled otherwise. The next thing that I want us to do is unusual, and even the creator of GeoGebra wasn't sure that this could be done. It's not perfect, but it's pretty sweet. And what I'm going to do is establish units in my algebra window, and I will be using pascals. But notice what I will say. I will just say pascals is 1, but then I will say megapascals is 1,000,000 pascals, and gigapascals is 1 times 10 to the 9th pascals. Why is that important? Well, in a problem that uses units in a variety of manner, it is very helpful to have the flipping of the scales of the units automatically, even though the program really doesn't use units. But I am doing this not for pascals and gigapascals, but for feet and inches later. I think that will be really helpful for us. The fundamental thing that I found is just to figure out what is your base unit. And your base unit might be feet for us later because buildings are in feet, or it might be in inches if we're looking at a stress analysis problem. But in this example, pascals is our base unit, and I will just say pascals is 1. You could use uppercase, lowercase, whatever, but it is case sensitive. Having established the base unit, I can say MPa is 1 times 10 to the 6th Pa, and gigapascals is 1 times 10 to the 9th Pa. Notice how it becomes blue in the input bar when it knows what you're talking about. I will also use mu, even though I'm not going to use it much, but we use it in this example, micro strain. So your author here is using micro strain, and strain has no units, but it's just 1,000,000th. Another super handy thing is that we can use the Greek letters. So you just find it over here. Here it is. And I will just say mu is 1 over 1,000,000. Okay. It didn't show up here, but that's under options, rounding, and you could just say, hey, give me... Sorry, options rounding. Oh my gosh, I'm trying to go too fast here. Let's say 3 significant figures, okay? The next thing is I want to establish the strains. And now in this problem, it's 90. I'm going to change the problem a little bit. So I'm going to make it like a demo. I'll just change it because this is your homework here. So I'm just going to make it 180 microstrains with a negative. So epsilon x is 180. So epsilon x is 180 microstrain. And this isn't a big deal, but now it knows what I'm talking about. If it can come up with a real symbolic fraction, it will. There's probably a way to turn that off, but I do it one by one. Go over to the algebra window that you want to change the fraction and right click and hit object properties. And over here under algebra, uncheck the symbolic and then close the property window. So now we're at 180 microstrain negative. And then in your homework, it's minus 30. I changed it over here to minus 60. I just made up some numbers here. Epsilon y is minus 60 microstrain. So again, it's not super built in, the units, but I like this. I think it's kind of sweet. And then I close the window. And then we had one more in our problem. Gamma was 120 microstrain. I just made it 100 microstrain here. So gamma is shear. Gamma xy is 100 microstrain. And again, I'll unclick the symbolic. You might even want to leave this open, but it takes up a little real estate. Okay, the next thing is I have a modulus of elasticity of 209 gigapascals. Here I'm going to make it 150 gigapascals. So E is 150 GPa. And then nu, the Poisson ratio. This one I couldn't figure out where it is. It doesn't look like mu in here. So nu, excuse me. So I'm going to just type in nu for the Poisson ratio. Nu is, and I made it 0.29. I think, yeah, it was also 0.29 in your homework. Not a big deal. And then sigma x is equation 1.4-5. This is just the stress transfer, the classic Hooke's law, stress in terms of strain. And it's a planar problem, so we don't have epsilon z. And I'm going to go ahead and put this in here. And if you double click on it, you could see what I did here. E over 1 minus nu squared times epsilon x plus nu epsilon y. So that's exactly what I'm going to do in this demonstration window. I'm going to say, I'll move it over here. I will say sigma x is equal to E over 1 minus nu squared times, and it's a space bar, or you could put in a star, but it looks a little nicer without the ugly star, epsilon x plus nu space epsilon y. Epsilon x plus nu epsilon y. Oh, I think I forgot to put a minus sign in here. My granddaughter calls those oopsie poopsies. Okay, so now sigma x matches my demo here. Sigma y is right there, another Hooke's law. Sigma y is E over 1 minus nu squared times epsilon y plus nu epsilon x. So the Poisson effect is on the transverse axis. And then tau xy, of course, is blah, blah, blah. Epsilon z is blah, blah, blah. The only other thing I want to point out in here, in interest of keeping the video short, is the matrix. So a matrice is kind of what you would expect from other languages, I would assume. Sigma, I'm going to call it sigma matrix, is, and just use curly brackets to embrace the entire matrix, and then curly brackets row by row. So I will say it's sigma x, comma, tau xy, which I don't have in here. Let's just say it's something 0, and then comma, whatever. Just put in, your numbers here. I guess that should be. I guess I'm being a little random here. 9,000. Sigma y. And then et cetera, et cetera, et cetera. So you can see that you would need three such columns, three such rows, excuse me, and three such columns for the sigma matrix and then the epsilon matrix. The only hint that I will give you on this problem is that there is no stress in the z direction, but it would be a fatal error to say there's no strain in the z direction. That's a very common mistake by students. The strain in the z direction does indeed exist. That's the Poisson effect. So the epsilon matrix has an epsilon z, but the sigma matrix does not have a sigma z. So the stress matrices, when we say complete stress strain matrices, that means it's a 3 by 3 for a plane stress problem. The only other new thing in here is download a PNG. You could snip things if you photograph it. You could scan things and snip it into a folder, and then it's under this button here, which is the penultimate button, and you're going to insert an image, and it's saying, hey, what do you want to insert? And you could insert a picture. It gives you these little dots here, the points, but you don't really need those. So that's exactly what I did. It's super, super powerful because we could actually do symbolic calculations here. We could solve equations. We could even solve ordinary differential equations. We could integrate. I'll show you how to do that next time. Okay.